Oh, hi. Today I would like to solve a couple of numerical solutions on induction machines. And here we have questions, as you can see. So it says the following observations are made on a three-phase 50 Hz Y-connected 380 volts RMS line-to-line induction motor with negligible stator winding resistance and core loss. Okay, and at no load the motor is rotating at 745 rpm. So we will think about that one. So if at no load the motor is rotating at that speed, that implies probably it's driven by 50 Hz. So you can say an synchronous speed should be like 750 rpm, because I think I forgot to write it here, but in the first part it asked for the number of poles, so I will use that information. So the stator cannot be started with a heavy load. So first you apply a high mechanical load to the motor, but it cannot start rotating because it cannot overcome that torque. So, but it only starts when the load torque is reduced to 236 Newton meter. So that implies, okay, let me draw the torque of a typical induction machine. It will be like that. So you cannot start the motor until the load torque is less than 236 Newton meter. So that means that is 236 Newton meter. If the load torque is less than that value, the machine will start rotating and it will create more torque. However, if it is more than that one, the load torque will be maximum, so either the motor will not start or it will start rotating in the opposite direction. Okay, so the next information that we are given is when the motor is running at the rated speed, we don't know that, the load is gradually increased. So it was, let's say it was running at that point somewhere, then it was increased, and it is found that the rotor speed reduced down to 600 rpm, but after it decelerates and stops. So for example, at first you were running here, so you just increase the load so it can give that torque at that point. Okay, so this is where you have T max. Okay, we don't know that value yet. At that point the speed was 600 rpm. So if you just increase the torque up to 600 rpm, the induction machine is managing keeping up with the load. However, if you further increase that one, then if you just drop down that curve, then it will start producing less and less torque, less than the load torque. Then it decelerates and stops. Okay, so in the first question, again, I didn't write it here, but what is the number of poles? Again, at no load it was rotating at 745 rpm. So S should be, 0, but probably there is a slight friction or that kind of losses. So NR is 745 rpm. And if this is a 50 Hz machine, it is given there. Okay, and if it is two pole, then remember it was 120 F times P, or 60 times F divided by pole pairs. Okay, so if it were a two pole machine, the synchronous speed will be 330,000 rpm. If it were a four pole machine, then it will be 1500 rpm. It goes like that. If it were a 8 pole machine, then it will be 750 rpm. Okay, so I know if it is rotating at 745 rpm, so it should be really close to the synchronous speed. So it doesn't seem realistic to have a two pole machine which the synchronous speed is 3000 rpm, but it is rotating at 745 rpm. The most convincing value, and of course you cannot have a odd number or real number value. It has to be an integer number of poles and an even integer. So I think it should be like 8 poles, and the synchronous speed is 750 rpm, but at no load it is slightly lower than that one. We will calculate those things, and probably that is because of the friction and windage losses. So at B and C parts, calculate the referred rotor resistance and total leakage reactance of stator and rotor. So how can we calculate that one? So the rotor core losses are eliminated. Okay, so we can use, again, the question it is given negligible stator winding. Okay, so R1 is again neglected. So let me try to draw the equivalent circuit. So we don't have parallel branch. Okay, so that one, normally that is where I have R1, but that one is neglected. It is given in the question. So I have X1, X2 prime, I have R2 prime, and I have 1 minus S over S R2 prime. Okay, and again, be careful, 308 volts line to line, and it is Y connected. So this is per phase equivalent circuit, per phase equivalent circuit. So if I am applying, this is 380 volts in the per phase equivalent circuit in a Y connected machine, the voltage here will be 380 volts divided by square root 3. Okay. Be careful with that one. So I know what information. I know the starting torque, I can use that one, and I know the point where the maximum torque is generated. And now, since it is an 8-pole machine, okay, I know the synchronous speed, it is 750 rpm. So let's try to use that information. So I know at maximum torque, okay, what was the condition for that one? The P gap should be maximum. Actually, we derived it in the previous lectures, and the air gap power, P gap, is actually the power transfer through those two components. Okay, so I know at the maximum torque I'm generating 600 rpm, so somehow I can calculate the value of these two components, right? So let's calculate the S at maximum torque point, right? So what is that one? We have 750 rpm synchronous speed, 600 rpm rotor speed divided by 750, that is equal to 0.2. So I have the maximum torque when the slip is 0.2, and I know T torque is maximum when P gap is maximum, and P gap is maximum from, if you have any problems with those assumptions and equations, please go back to our slides. So P gap is maximum when maximum power transfer is satisfied, and the condition for that one, P gap, again for that one, is max if I know that one is neglected. So you can think this is like a source, and this is like the source impedance, and this is my load now. This is my load impedance. So that one normally I write R1, X1, X2 equivalent impedance should be that equal to that one. But in our question, R1 is neglected. So I can write X1 here. X1 plus X2 prime, okay, that should be equal to R2 prime plus 1 minus S over S R2 prime. So actually you can remember that one, the combination of these two is equal to 2 prime over S. So from that information and that information, I can write X1 plus X2 prime, okay, that is equal to R2 prime over 0.2, or alternatively I can write 5R2 prime is equal to X1 plus X2 prime. So that is here. So that is, the first thing that I can use. But again, that information is not enough to get actual values. But actually I used the maximum torque information, the position where maximum torque occurs, and I managed to find a relation between the X1 and X2 prime and R2 prime. So how can I use that information? So at that point I know slip is equal 1. So I can write the torque expression, write the slip is equal 1, and I know the value, I know the voltages. So let's try if I get another expression with equivalent circuit parameters. Okay, so I know T starting is equal to 236 Newton meter, and starting torque means NR is equal to 0, so that means slip is equal to 1. Okay, so torque is equal 3 V1 square or V20 square, whatever you call it, and right, R1 plus R2 prime over S, okay, squared. You don't have to memorize that equation, okay? So times that one. Again, if you don't remember professional life, don't worry, this is V1 divided by all that equivalent resistance actually gives you the current here. Okay, so and you want to calculate the power dissipated in that two components divided by omegas, or more specifically you want to calculate the power dissipated in that component divided by the rotor speed, and that if you divide those things, slips cancels out and you get that equation, and that one is the synchronous speed. But whenever you have torque, okay, don't get confused, it has to be the mechanical synchronous speed. So here we have a number of pulses different from 2, so don't put the electrical synchronous speed. Whenever we are talking about the torque, we are now in the mechanical system. So if you are dividing power by speed to get the torque, remember power is equal to torque times speed, but that speed is always the actual mechanical speed, and it is not again in RPM, it is in radian per seconds, but in mechanical speeds. Okay, so let's put our equations there. And you can start writing the V1 value, but again we don't know the actual values of the components. We know R1 is eliminated in the question, but what I know is instead of X1 and X2 prime, I can write 5 R2 prime. Okay, so let's do that. So let me put that equation 3v1 square divided by s, and in that condition the slip is equal to 1, so I will put s is equal to 1, and also I will put that value. So I have r2 prime over s is equal to 1, so this becomes r2 prime square plus x1 plus x2 prime square. X1 plus x2 prime is equal to 5r square, so this becomes 25 r2 prime square, okay, times r2 prime over s is equal to 1, times 1 over omega s. Okay, what is omega s? So omega s is equal to 2 pi electrical frequency. This is mechanical, again, synchronous speed. So I need to divide it by pole pairs, okay, pole pairs. So if we have, remember, we have 8 poles, okay, we had 8 poles, so the actual mechanical speed will be 1/4 of quarter of the actual speed. So it is 2 pi times 50 hertz divided by 4. Okay, so I will write that omega s here, and for V1, remember it was 380 volts divided by square 3. So let me put all those things, and actually you will see, don't have to, those will cancel each other. So I will have 25, 26 r2 prime square times r2 prime divided by 2, let me write it like that, divided by 4. That one cancels, so that 3, that one, they cancels each other, and actually if you do that calculation you can find r2 prime is equal to 0.3 ohms. Okay, and if you want r2 prime is equal to 0.3 ohms, x1 plus x2 prime are 5 times of that value, so I can write x1 plus x2 prime is equal to 1.5 ohms. Okay, so we completed the next this part, so let's move on to the next part. Okay, in the next part we are given the rotational, I think I should write rotational friction. Okay, if the rotational friction power is 1518 watts, find the air gap power, rotor copper loss, internal mechanical power, or the gross mechanical power. You can say like it's the gross mechanical power, and the net output power when the rotor is rotating at 712.5 rpm. So let's try to calculate that one. So I know nr is that, and I know the synchronous speed is 750 rpm, so that one is still connected to 50 hertz group. So I need to calculate the slip. Okay, so it is that value minus the rotor speed divided by 750. Okay, so this is 37.5 divided by 750, so this is 0.05. Again, it is kind of realistic, it's like 5%. So again, in the exam or in your professional life, just once you make that kind of calculations, please ask yourself if it is feasible or not. I don't know, for example, I can make a calculation error. Instead of 755, I can get 7.5. Then the slip will be 5, okay, and 5 is not realistic, okay, so it shouldn't be in the that kind of range. Or if I find it like 0, then that means that cannot produce any power, or if it is in the negative range, maybe that should be set in operating in the motoring range. So please ask yourself if those numbers make sense or not. So let's try to calculate the power and torque. So let me draw again the equivalent circuit. So let me draw it fully. So normally we have the stator resistance, but this one is again neglected. R1, that one is neglected. So we have x1, x2 prime, and we calculated these two in the previous part as like J 1.5 ohms. Okay, this is J, don't forget the J's. And R2 prime is 0.3 ohms, and this was 1 minus S over S times R2 prime. So I know the S, I know the R2 prime, so I can calculate that one. So 1 minus 0.05 divided by 0.05 times 0.3, and if you make that calculation, you will find it like 1.7 ohms. Okay, so I know actually that voltage level, this is 380 divided by square root 2, so I can calculate the current value, right? So in order to find the current, I need to divide that voltage into equivalent impedance. So let's do that. So current is 380 divided by square root 3. This is 1.5, this is 0.3, this is 5.7, so that makes 6. And remember, it was R2 prime over S in the equivalent, and you can quickly double check 0.3 divided by 0.05 is actually again 6. So it is square root, don't forget the J's, you cannot add these things directly, so instead it will be 6 square plus 1.5 squared, right? So you need to find the impedance, and it's a RL circuit. So if you do that calculation, you can find 35.47 amps. Okay, so I find that value. So the question asks about the air gap power, rotor copper loss, mechanical power, and the net output power. So in the system, let me draw here. So that is our motor. Okay, so we are giving some input power, and normally I have my P stator loss, but we don't have the series windings or the parallel windings. Actually, that is eliminated, but we still have the rotor loss, the rotor dissipating through that element, and it is not shown in our equivalent circuit. But after that one, once you subtract these two values, you have the P gross. Okay, but then after P gross, then you have the friction power, and then you have the useful net power. Okay, and another important thing is that is per phase equivalent circuit, so don't forget to multiply it by 3. Cool. And actually, in order to find the input power, you cannot again multiply that value with that value and write it as a power, because there is a power factor, and this is just the magnitude. Okay, this is magnitude, RMS magnitude of the current, so we don't know the power factor. Yes, you can calculate. Yes, you can calculate, but in this question, you don't have to. So let's, if I know current, I can calculate the gap power. Through here, the real gap power, because these are all resistive components, so I can multiply the current by the resistive components. So I can write P gap is equal 3, this is the per phase equivalent circuits, square I square times R2 prime over S. So it is the combination of these two. Okay, so let's do that. 3 times 35.47 square times 6, and this is 22.65 kilowatts. So in the gap power, I'm dissipating that much. And P copper, the rotor, so that is the power dissipating on that element, or it's shown here. That can be calculated as like 3 I square times R2 prime, it is that element, and it is 335.47 square times 0.3, so it is 1.13 kilowatts. So you are dissipating over 1 kilowatt over that resistance. That resistance is heating the rotor. Okay, so let's calculate the mechanical or gross power, P gross mechanical. Okay, that one is 22.65 minus 1.13 kilowatts, and that one is equal to 21.52 kilowatts. Okay, so then you need to subtract the friction to get the net power. P net is equal P gross minus P friction, and friction is given in the question as like 1.52 kilowatts, sorry. So you can subtract 21.52 minus 1.52, that is equal to 20 kilowatts. So that is the useful shaft power. So now again here the P gap. So normally if I know the P gap, in order to find the input power, I need to add the P gap, I need to add the 3I square R R1 or stator copper losses to find the input power. But in our question, R1 is neglected, so P gap is also equal to, in our system, there is no stator loss in our system, P in is equal to P gap. And again, if you use that method, you don't have to bother with the power factor or the phase. Okay, or alternatively, what you can do is, the impedance angle of those circuits, so you can actually calculate, the value of the j omega L components and resistive components. So you can calculate the phase of I, it will be lagging. So by the power factor, you can multiply 3 times that voltage times current, and you can get the real power. But don't start your input power calculations by directly multiplying these two. It will be wrong because of that inductive components. But actually, if you just go, start from the gap power in this question or in some questions, you have the mechanical power, and real power is only dissipated in resistive components. Okay, the capacitors or inductors cannot dissipate or absorb real power, they absorb reactive power. But in real power calculations, you can just move on by calculating the resistive components. So let's calculate the efficiency. So this is my output power, 20 kilowatts. So that is my input power or gap power in this case. So efficiency, okay, and can be written as like output power divided by input power, and 20 kilowatts divided by 22.65 kilowatts, and this is 88.3%. Okay, so again, this is kind of realistic, and if you happen to find anything larger than 100%, that is definitely wrong. Please, don't put in your exam papers or anywhere efficiency is larger than 100%. Or if you happen to find something around 20%, 5%, 1%, that is probably wrong, or that's a really badly designed electrical machine, because that will be more efficient as a heater than electrical motor. Okay, 80-90% in an electrical machine, that's good and that's realistic. Okay, thank you.